Okay, so getting into the kind of the back half of this, we want to talk about temperature because in getting to temperature, we're going to be able to just kind of touch on these ideas of energy, which are going to be kind of where we're going to have probably the most problems in this chapter. So what is temperature? Temperature is a measurement of the hotness or the coldness of an object. And we can use temperature to predict which direction heat is going to flow in space, because heat always goes from a hot object to a cold object. And so if I've got two objects and one of them's 100 degrees and the other one's 20 degrees, you can guarantee that the hot object is going to get cooler and the cold object is going to get warmer until they get to some kind of meeting spot in the middle. That's the direction that heat flows. It always flows from hot to cold. Now, we measure temperature using a thermometer. The type of thermometer that we use, well, it depends upon what we're trying to figure out. So in the laboratory, we tend to use Celsius thermometers because in scientific kinds of discussions, Celsius is the way to go. And we'll get into that more in a second. Here in the United States, almost every temperature measurement that we take is in Fahrenheit. The history of that is a long and tortured one. We won't get into that today. But for our purposes in this class, we're going to take a look at 3 different temperature scales. The Fahrenheit scale, which we are probably the most familiar with. The Celsius scale, which we should have at least some familiarity with just because we've at least heard of it. And if we've traveled to anywhere outside of the United States, we've seen it in those places. And the Kelvin scale, which I'm going to guarantee most of you have very little familiarity with unless you've taken a more significant science course in high school. Now, the thing that these scales have in common is that they're all based upon the boiling point and freezing points of water. These first 2 scales, Fahrenheit and Celsius, these are what are called relative scales. And the reason they are called relative scales is because they are based on defined values. The defined values being the boiling point and the freezing point of water. So the Celsius scale permanently and purposefully defined the freezing point at 0 and the boiling point at 100. The Fahrenheit scale did something similar, only 32 and 212. The Kelvin scale is actually very similar to the Celsius scale. You can see that on the on the Kelvin scale and the Celsius scale are essentially the same. 100-degree difference in Celsius is the same as a 100-degree difference in Kelvin. Why the Kelvin scale is set this particular way has to do with what is called the 0 point on the scale. The 0 point on that Kelvin scale is an important one. You've might have heard of this. This is called absolute zero. Absolute zero is a defined spot where all molecular motion, all atomic motion stops. So even in the coldest of ordered solids, there is still some molecular motion taking place. You know, we may not have a whole lot of it, but at the very least, those solid molecules are still vibrating around a little bit, even if they are fixed in this place, even at really cold temperatures. But at 0 Kelvin, that is the theoretical mark where even that small amount of molecular motion doesn't exist anymore. Now, we can't say that this is something that we have observed. Absolute zero has never been actually observed. It's kind of impossible to get there. Just because no matter how good we insulate something, there's always going to be a place where a little bit of energy can come in, and that little bit of energy is going to just raise that temperature ever so slightly above absolute zero.
How cold is that?
Oh, you're putting me on the spot here. Let's see. So on Celsius, it's negative 273. Fahrenheit, I want to say it's negative 474 or something along those lines. We can actually do the calculation here in a second.
So everything's frozen, all matter.
Everything.
So back to
Yeah. Right. So yes, absolute zero is a theoretical value. It's not an actual value because we can't prove its existence. And to go back to something you said earlier, Sean, there are exceptions to every rule. That exception doesn't even apply to certain types of elements that are theoretically supposed to have molecular motion even at absolute zero. That's well above the scope of this course and well above the scope of my knowledge, but nonetheless, it does exist. All right. What is the temperature where water freezes? Right, 0 degrees Celsius. What is the temperature where water boils? So we know it's either 212 degrees Fahrenheit, 100 degrees Celsius, or if we add 273 to that, that would be 373 Kelvin. How many Celsius units between boiling and freezing for water? 100. Okay, so here's where we get into kind of the more difficult stage for today, because we're going to have to use our calculators here. Now, the good news is these temperature conversion calculations are not too terribly difficult. These equations will be given to you on an exam. And when you're taking the quiz for this, be sure to have that jotted down somewhere, because even though you're taking the quiz in mastering is going to shut off your access to the ebook and other stuff when it does. It's just kind of, that's a quirk of the system. So make sure that, you know, if there are any calculations that you have or that you need, make sure that you just got them jotted down somewhere for easy reference when you go to take the quiz. Like I said, in an exam situation, this is the kind of stuff we would give you. So how do I convert between Celsius and Fahrenheit? Well, this is one of the equations that we can use. So Fahrenheit is equal to 1.8 Celsius, 1.8 times Celsius rather, plus 32. If I had to go the other direction, to get Celsius, I would take Fahrenheit minus 32 and divide that by 1.8. And finally, if I wanted to do Kelvin, Kelvin is Celsius plus 273. And if I wanted to flip that around, then I would take the Kelvin and subtract 273.
There's certain when you go from Fahrenheit, you have to go Fahrenheit, Celsius.
So if you want to go from Fahrenheit to Kelvin or vice versa, you have to do it in 2 steps. Could you do it in 1 step? Yes. I mean, if you're that strong in algebra that you could, substitute one into the other and solve, you could do that. It's easier to, especially since Celsius and Kelvin are just 273 apart. It's a lot easier to just convert Celsius to Fahrenheit or Fahrenheit to Celsius and then do the adding or subtracting. All right, so let's look. Yes. Okay, so different how? Did they use? Multiply by 5/9. Okay. Yeah, so they are the same. Well, okay, so what, don't mean to cut you off there, but so the fraction 9/5, 9 divided by 5 is equal to 1.8. And so okay, well, I would say that the fractional way that you're talking about, 5/9 and 9/5, that is probably the more generally used way. However, the reason I'm presenting you 1.8 instead is that I have found personally that when it comes to multiplying and dividing by fractions, it's a lot easier to make a mistake multiplying and dividing by fractions as opposed to multiplying and dividing by 1.8. And so from a standpoint of accuracy, they're both correct. From a standpoint of simplicity, I feel like this is simpler. And if I have an option to do something simple, I'm going to take that option to do it simpler. So that's more of a personal preference thing on my side, but that's where I operate. And so when it comes to answering this kind of problem here, 34.8 Celsius, what is that in Fahrenheit? Well, with this equation now, I can do that calculation. Fahrenheit is equal to 1.8 times 34.8 plus 32. And if I do that calculation, 1.8 times 34.8 gives me 62.6 plus 32 would give me 94.6 degrees Fahrenheit. So it really comes down to, if you've got this bank of equations at your disposal, it's just figuring out which one is the correct equation to use. And since we've already done kind of all the algebraic flipping around, really it's just a matter of which one allows me to solve without having to flip around the equations or do extra mathematical steps. Let's take a look at a couple other examples. On a cold winter day, the temperature is -15 Fahrenheit. What is that temperature in degrees Celsius? So we're going to try to take -15 degrees Fahrenheit and turn it into degrees Celsius. Going back to our chart here, what's the best way to do that? Which equation gets us there the easiest? I could put it in here, but I would then have to subtract 32 from each side, divide by 1.8 to get that TF by itself. That equation we wrote to the right is the easier equation to use. So TC is equal to TF minus 32 divided by 1.8. -15 minus 32 over 1.8. Remember, this is in parentheses, so I need to do it first. So that's going to give us -47 on top, divided by 1.8. It's going to give us -26.1 degrees Celsius. So that would be letter D here. Now, one really important note here always comes up, it's worth mentioning. When you do calculations like these, your calculator is going to generate approximately 3.2 million decimal places after the calculation. How much of it matters? Well, we're not going to get into a discussion of significant figures. That's well beyond the scope of this course. But what we can kind of use as a general rule of thumb is this. If I have a measured value like that, I'm just going to match the measured value. So the measured value here was -15 degrees. It had no decimal places. It would make sense that my answer here also had no decimal places as well. And so that -26.1, I could easily just turn into -26. And that's where the answer that we got comes from. So don't twist yourself up trying to mark down every single digit that comes out of your calculator. Chances are most of them aren't important. Just kind of use a general rule of thumb here. However many digits, whatever that number looked like before we did the calculation, try to make the number that comes out of the calculation look like it. All right, any questions here with this first sample problem? All right, try this one yourselves then. What is normal body temperature of 37 Celsius in Kelvin? All right, let's see how we did. So the equation that we want to use is this one on the bottom left here. We're turning Celsius into Kelvin, so we need to add 273. 37 plus 273 would give us 310 Kelvin. That's letter B. All right, so out of this section, that's really as far as you have to take it. Can you go between Celsius and Fahrenheit? Can you go between Celsius and Kelvin? And if you can do those calculations, not going to be too much that I can throw at you that you won't be able to do. That being said, any questions about temperature and conversions before we move to energy? All right. So as we get into energy, we've got to make sure that we get our definitions right. In probably the most kind of set forward, straightforward way, we talk about energy as the ability to do work. Now, what that work is depends on a lot of different factors. Work can be the literal act of moving an object from one place to another. That is work. Work can be the idea of causing a gas to expand or contract. There are lots of things that can kind of be in it and involved in it. Yes, it makes objects move, it makes objects stop. There are forces and things that go into it. But when it comes to energy, we tend to break it down into two big, broad categories. The first, kinetic energy, the energy of motion. When things are moving, they have kinetic energy. When things are not moving, they don't have kinetic energy. So there are lots of different examples of kinetic energy. Your book gives you the examples of swimming, water flowing over a dam or over a hill, a waterfall, the act of physical motion and movement, working out, going for a run, riding your bicycle. All of that's kinetic energy because you are in motion to do all of those things. The other kind of energy is potential energy. Now, we can think of this energy as energy that is stored up inside of a substance. And because it is stored up inside of that substance, we tend not to think of it as energy of motion, but rather as energy that could get converted to kinetic at some point. And the amount of potential energy that something has is largely related to a number of different factors. One of them just being near position. I hold this marker here at my chest. It has a certain amount of potential energy. If I were to drop it to the ground, it would gain speed until it hit the ground. But if I hold it at a higher position, we would all agree that by the time it hit the ground from here, it would be going faster than if I dropped it from here. That's a difference of potential energy. It has more potential energy in this position up high than it did here at my chest. And certainly more than it would have if I was holding it just a bare inch above the table. So a lot of times potential energy is about energy of position. Sometimes it's just about a matter of configuration. So for example, if I've got a spring that is compressed, well, it's not doing anything at the moment, but if I release whatever is holding it in that compressed position, it will open up. And from a chemical standpoint, we can think of potential energy in the form of bonds. Those things that hold atoms together to make molecules, those things that hold ionic crystals together to make salts. Well, there's potential energy in those as well. And if we were to release that potential energy in some kind of way, that would be the makings of what we would call chemical energy. That is the energy that causes heat, light, sound, that we associate with chemical reactions. Yes, yeah, that's a good way of putting it. So if I'm looking at this pen, right now it's not in motion, but if I were to release it, it would be in motion. It had the ability to go down to the floor here. Potential up, kinetic when it's not, when it's moving down. Now that it's on the floor again, it has neither. The only kind of energy it would have is if I were to move it myself, it had no potential energy. All of the energy that went into it came from me. When it started moving again, because I kicked it, then it was kinetic. So movement is kinetic. Positional is potential. It's possible to have neither. So right now, that pen sitting there in the corner is at rest. It has no positional energy. It can't drop any further. It's not going to move on its own from that spot. The only way we could get it to move is if we introduced more energy to it to force it to move. All right, other questions? Okay, let's go through these together. This is, anybody still rollerblade? I mean, that was a thing when I was a kid, but let's not get into that. All right. Would rollerblading be an example of potential energy or kinetic energy? Kinetic, unless it's in my case where they are just sitting, hanging up in my parents' basement, in which case it will never be kinetic again. It will always be potential. All right, a peanut butter and jelly sandwich. Well, unless it grows legs and walks, it's going to have potential energy in it. That potential energy isn't in its ability to move, but rather what's stored up in its chemical bonds that can be converted into chemical energy upon when we eat it. Mowing the lawn. Absolutely, we are moving and moving and moving. Gasoline in your gas tank. Potential. We're talking about the potential of that gasoline to be ignited and cause the motor to move. But if it's just sitting in the gas tank, it's at rest. It's not doing anything at that moment. The only thing it could have is potential energy. All right. Heat. Now, heat is a form of energy. Heat is the energy that's associated with the movement of particles. So in some ways, we can think of heat as being on the kinetic side of our energy. Maybe not necessarily in terms of like, I can see that this pen is moving, but more on at the molecular level, the particles inside of this marker are moving, even if we can't see them. They are moving at the subatomic, the particular level. Heat would be a way of measuring just how much they are moving. The faster particles move, the greater the thermal energy inside of that substance would be. Now, heat is measured in a unit called the joule, which is given to us by a capital J, or calories, which are given to us. The unit abbreviation for calorie is lowercase cal. Now, I make mention of lowercase cal because there is a uppercase cal that exists as well, and we need to be able to distinguish between them. And we'll talk about that in the last section here that we talk about today. There is a relationship between calories and joules. Every calorie is exactly 4.184 joules. Now, why the two definitions? Well, they come from two different eras of scientific thought. So calories come about, they are defined as how much energy does it take to raise 1 gram of water by 1 degree Celsius. Joules have a more, they're derived out of the international system of units. So that's why we have the two different unit systems. That's how they're related to each other. Now, one of the things that you're going to be asked to do in this chapter is converting between joules and calories. And that's why we gave you these conversion factors here. And we'll do a little bit of practice with just that. So here's our first practice problem. How many calories can we get from a pat of butter if it provides 150 joules of energy when metabolized? Okay, so we want to convert 150 joules to calories. Now, really, there are two ways that we can go about doing this. Which one you choose really comes down to what are you the most familiar with? What are you the most comfortable with? Your book is going to favor something called the factor unit method or dimensional analysis. And how that works is we start with our measured value and we use this conversion factor and we multiply. And the one we multiply by is going to be the one that allows us to put that unit in the denominator and the unit that we are converting to in the numerator. And so if you do this, you can see I've got 1 times 150 in the numerator. And in the denominator, I've got nothing here. So I've got 1 times 4.184. And so if I do my canceling here, joules cancel. I'm left with calories. I just need to do the calculation itself. $150 divided by 4.184 would give us 36 calories. So it would be C. Okay, so this is the method that your book is using. Where this method becomes kind of useful is if you had to do a lot of these conversions one after another, after another, after another, because that would mean that you'd be able to keep track of the units as you went. Since most of the calculations that we are doing involve just one conversion, an alternative way to do it would be to use proportions. And with a proportion, you've probably seen these in math. I have 150 joules that I'm trying to convert into calories. And the conversion factor says that there are 4.184 joules in every 1 calorie. Well, to solve a proportion, you cross multiply. So 4.184 times x is equal to 150. And so x would be 150 divided by 4.184, which would give us the same 36 calories. So since our conversions are only one step most of the time, you could really go with either direction and be completely okay. Obviously, if we had to do 4, 5, 6 conversions in a single problem, we could see where this proportion method would kind of really just be awful to have to solve 4, 5, 6 proportions just to do one problem. But again, for the most part, this isn't too bad to do if you're kind of approaching it this way. All right, any questions about either one of those techniques? All right, so in your post-lecture and on that quiz, you're going to see some of those calculations. You're going to see them in that dynamic study module as well. The last bit of information that we have out of chapter 3 is just concerning the idea that calories also apply to nutritional values as well. The only difference is that the nutritional calorie, the one that is spelled with a capital C and the unit that has a capital C, is 1,000 of the calories that we were just calculating with. So when you look at a nutritional label and it says that there are 120 calories in a serving, that's 120 nutritional calories. From a standpoint of energetic calories, the ones that we were just talking about, it'd be 120,000. Now, one way that we kind of get around this is that when we talk about nutritional calories, we often talk about kilojoules instead of joules, so that the conversion stays exactly the same. It's 4.184 to 1. Only it's now kilojoules and kilocalories, nutritional calories, instead of joules and calories. The other important piece of information for our purposes here is that when it comes to food calories, when it comes to nutritional label values, how they come up with those values for 120 calories per serving has to do with this formula here. Every gram of carbohydrate in a sample of food is worth 4 calories, 4 nutritional calories. Every gram of fat, 9 nutritional calories. Every gram of protein, 4 nutritional calories. And so what they can do is if you add it up, 4 times 9 is equal to 36. 19 times 4 is equal to 76. 2 times 4 is equal to 8. 76 plus 36 plus 8 gives you 120 calories in total. Now, it doesn't always work out this neatly. You can see they've even taken some liberties here. Calories from fat, 35. It's actually 36. There's a little bit of rounding that goes into it. So usually they round up to the nearest 10. Just because they like having that nice round value on the box label itself. All right, so the last thing is just the same kind of calculation that we were talking about. If I wanted to look at the number of calories in a sample of milk, 13 grams times 4 would give me 52 calories for carbohydrate. 9 grams times 9 would give me 81 calories for fat. 9 grams times 4 would give me 36 calories for protein. 52 plus 81 plus 36 is 169 calories, which on the label would have been rounded up to 170. All right, we made it. We got through it all. So what I'm going to ask you to do, we're going to keep the schedule as it is. If you have questions that come up, don't hesitate to send me a message, drop me an email, throw a text my way, or show up to my office tomorrow and ask about it. I'm not going to see you again until Tuesday, so we're really not going to have a chance to talk out any of this stuff that you might run into before then. So take advantage of those other ways of getting in contact with me if you get stuck on stuff. Otherwise, enjoy your weekend, enjoy your Monday off. I'll see you on Tuesday.